All right, hello everyone. Welcome to Chapter 5. In this module, we're actually going to be covering Chapter 5 and 5S on this one lecture. There are a few more slides than normal, but some of them I'm going to be showing them to you, but we're going to be doing the quantitative pieces, the math pieces of it on the separate video where we go through the solved problems, and I'll go through some of the problems from the slides, break those down for you on that video. So we'll kind of breeze through those ones. So even though there's more slides on this one because it is Chapter 5 and then the supplementary chapter, which is Chapter 5S, we're not going to be staying on those slides as long as we might on some of the other lecture points. So Chapter 5 is about strategic capacity planning for products and services. Basically, how much equipment do I need? How much space do I need? What skills do I need for my employees? So capacity is the definition from your book is the upper limit or ceiling on the load that an operating unit can handle. Okay, how many parts per hour can this machine produce? Right? How many units can we store in this place for inventory? That's capacity, the absolute upper limit. Now, there's a few different types of capacity, meaning what are we planning on it actually being utilized for, or what it can effectively do versus what could it theoretically do if we were to have all the other needs we need to make that happen. So equipment, space, and employee skills are types of capacity. The questions during capacity planning you need to ask yourself are what kind of capacity, how much do we need to match the demand? So that's where it comes back to Chapter 3. If we can't forecast demand accurately, then we can't make this decision very well. If we don't have a good idea for what demand is going to look like, then our decisions for capacity are going to be poor. So a reason why forecasting is right up in front in this book is because we hearken back to that throughout the rest of the semester. When is it needed? When do we need to complete the building of it? When do we need to have this much production capability? Those need to be asked. And of course, one of the related questions always comes up is how much is it going to cost? What benefits and risks would I have? And then can the supply chain handle those changes? If I'm planning to all of a sudden have this much more supply, can I actually get it to my distributors? Do I have a way to do that in a way that makes sense, or will I just have all this backload of inventory because I've increased my capacity by so much, but I have nowhere to send it? So capacity decisions are typically considered strategic because they are in the long term. You have to make these decisions early on. They're not short-term decision makings because they are typically huge projects, huge cost. It could be as big as building a brand new facility and then planning the capacity in that way, or doing a whole new expansion, or hiring a bunch of more employees. They require you to commit resources for the long term as well for them to succeed. You have to plan them far in advance because they just will eat up your finances. You have to have the entire organization on board for these capacity decisions. Your financial team has to be there to ensure that the finances will match up with the needs for the cost every step of the way of the building of the new facility, or the installation of new equipment, or training. That your marketing team is spot on with their forecasting, right? So capacity, we want to use typically units, number of products, something that doesn't require updating. Measuring in terms of dollar amounts of sales is problematic. It asks you, why is that problematic? Well, because the value of a dollar changes over time, through inflation, through political turmoil. You look at some countries where it takes 2 billion of their dollars to equal $1 because the faith in the government backing of the dollar is so low. So the value of a dollar can change over time. So that's why it's typically better to measure capacity in terms of units of production. That would be the simplest way and the most accurate way going forward of being able to compare it. And then when we look at capacity, I hinted at this, you've got the design and the effective capacity. So the design is how much could this facility do at a maximum output? If we could get every unit produced that this thing could produce, provided we have enough resources to actually do that, meaning employees, raw materials, scheduling needs, inventory to put it, whatever the case is, what is the maximum we could do? That's what it's designed to do. However, there is an effective capacity as well, and this is more reasonable measure of capacity because you've got employees that your employment level is going to vary over time. You've got scheduling reasons, time off, equipment needs maintenance. Maybe you don't necessarily need to have this much production year round or whatever the case is. So effective capacity and design capacity are the two types. And with those two types, we're going to look at two types of output: efficiency and utilization. So your efficiency is how much output you have divided by your effective capacity, meaning we probably are only going to put out this much at a maximum, but how much am I actually going to put out? If I have enough people that I could put out 100 units in a day and I put out 80 units, then you would divide 80 by 100, okay, and you'd get 80%. However, if the machine actually could do 160 units and I'm putting out 80, I'm utilizing half of the capacity, 80 over 160. Now, the efficiency matters because it's what the business is likely to do. And then we can see how well our staff is actually accomplishing that goals. Utilization would be more for knowing how much excess capacity I have in case I wanted to maybe do some work for another company. I could maybe use my equipment to produce a similar good for another company and they could pay us a fee. So knowing how much extra capacity you technically have and could use under the right circumstances is important too. And if you are having trouble remembering which one is efficiency and which one is utilization in terms of effective capacity and design capacity, I think as a mnemonic device, it'll help to look at the first three letters of effective and the first three letters of efficiency. EFF matches up. So only one way will it match up. If you're trying to remember which one's which, okay, do efficiency actual divided by design, utilization actual divided by effective? Well, utilization and effective don't match. Efficiency and design don't match. So that might help you to keep track of it. I'm just thinking, you don't have your notes handy and you're trying to remember which one's which. Effective capacity and efficiency, those first three letters do match up, and that might help you keep it straight. All right, here's an example. I just kind of went through that. You could get 40 truckloads out per day, or you could get 50 out, but normally you would expect to get 40 out based on demand. If you actually got 36 out, you have 36 out of 40, so you're at 90% efficiency. However, you do have capacity. You do have 28% of your capacity left over. So if you were to hire temporary workers or outsource, hiring temporarily, or bring in a bunch of resources or pay overtime, you could actually get out several more there. The facility space, the process factors that you have put into place, your operations team, policies that your company has as far as we won't pay overtime at all, or we'll only pay this much overtime, could factor into your effective capacity. Or maybe the number of people you'll have scheduled on a shift, or policy on whether or not to allow PTO usage or vacation uses during times of high productivity could affect your effective capacity at any given time. Ways to enhance your management of capacity is when you design a product and you are building the space to make that product, designing flexibility into the systems in advance and looking around and saying, what else could this equipment do if we made it a modular system that we could swap out a part and make this other thing? Could we then be able to use our capacity with one piece of machinery, and during the time we're not making our main thing, we could swap out a piece and make something else for another department or another product line. Knowing the overall life cycle of the product, how long that's planned to be in use, would be important in terms of knowing how much to invest in certain pieces of equipment. So about bottleneck, this term comes up a lot, but a bottleneck, once again, is any operation that lowers the capacity, or whose capacity is lower than the rest of it, which would lower your overall capacity. If I needed to make these 4 things and they all led through to here, well, I'm getting all 4 of these done at once. They take 10 hours a piece. And so I have all 4 of these components ready to go, but this one operation takes 30 hours. Which makes all these other operations in effect take 30 hours as well, right? Because this thing is slowing it down the entire thing. So better design plan, or maybe additional equipment for this step. That way you can do 2 at once instead of 1 at a time, would help your overall operations. You can look at the cost there, and we'll look at that in a later chapter a little bit. Economies of scale, the idea that if you can increase your output rate, then the cost per unit on average goes down. Reasons this happens because you have the fixed costs, whatever it costs you to build that equipment or to even turn on the lights in your facility is fixed. But if you make more units, you can say that you've made this many units for this total cost instead, and then if you have that many and you sell, you're able to sell them in bulk for higher margins. Diseconomies of scale would occur when you don't make as much to cover the costs, and so the average cost per unit, when you take the total cost and divide it by the number of units you produced, finding the cost per unit goes up. Evaluating alternatives. So this is going to come up in chapter 5 and 5S and several chapters down the road. The idea alternative is when you have 2 choices or more to make. Okay, I can do this or I can do that. Those are alternatives, right? Simple. And you're evaluating them, economically speaking, how much will it cost is a big one. How soon can we have it? Because if we can't meet demand, even though the price is right, then it's not a good decision there. Will there be additional costs down the road? Continuous operating and maintenance costs be, and then non-economic reasons for choosing one of 2 options might be public opinion. Yeah, I could do them here for this cost, or I could lease them out to a sweatshop in another country for a lower cost. But the public opinion on that's going to be probably pretty poor, and maybe your company can't weather that storm, and it's also not the right thing to do, so you choose not to do it. So this should look familiar if you've taken a finance class or other classes that look at costs in business. But your total costs are equal to the fixed cost plus the per unit cost. Fixed cost plus variable cost is your total cost. So the variable cost would be, let's say I had to buy this piece of equipment and it cost me $100,000, and then it makes these little parts, and every one of those parts cost me $1 a piece. Well, if I make 50,000 of those parts, then the total cost to make 50,000 parts isn't 50,000 times $1. I have to add in the cost of the equipment as well. So I add in 100,000 plus the 50,000 units for $1 a piece for $150,000. That's my total cost to produce that much. But the fixed cost, that's constant. So no matter how much I make, effectively I start in the hole, right? If I haven't built this equipment, then I'm down $100,000 until I start producing enough units to break even. So let's talk about break even point. There's a certain amount of volume of output at which the total revenue that I am producing is going to be equal to the amount that I had invested in that equipment to begin with. So if you look at your fixed costs, let's say I'm in the hole for $100,000, right? Because that's what it cost me. Okay, so $100,000 in, oops, here we go. $100,000 in fixed cost, right? And then for every unit that I make, the variable cost is $1, and then I sell it for $5. Okay. Well, if I'm selling it for $5, but it cost me $1, the difference between what I'm going to sell it for and the amount that it cost me to make, that's basically the amount at which I'm digging myself out of that $100,000 hole, in this case, $4 at a time. So I'm selling a product for $5. It cost me $1 worth of material to make it. I'm making $4 at a time. And if I divide $100,000 by 4, I get 25,000. And so the question as far as break-even point in units would go is 25,000 units. If I make 25,000 units on this piece of machinery and I sell them for $5 a piece and they cost me $1 a piece, then at that point, I'm dead even. I have made $0 in profit and $0 in cost. Your total profits are 0. That's what you that's an important number, right? That's when you're no longer operating in the red and you're starting to move over into operating in the black. We can see in here the break-even point. If you were to map that out, you're at a loss, you're at a loss, you're at a loss. All of a sudden, you're in the profit as soon as you cross this point in terms of units made. We're going to skip over those top 3 ones. At one point I want you to be aware of, because it's going to come up in your homework, is what's called the point of indifference. Point of indifference is, let's say you're looking at 2 different alternatives, this choice or this choice. Well, maybe one has a higher fixed cost, but one of them has a lower variable cost. So if you make a certain amount of units, one is going to have cost you less money. But once you get to a certain point in units produced, the other one is going to make you more money. However, there exists a set point, a specific number of units in which if I make exactly this much, then the profit's going to be equal. And that point is called the point of indifference, because if I'm always going to make this many units, then I could go with either choice, because either choice is going to lead to the exact same amount of profit. There's only one unit amount at which that number is true. So that point of indifference will be important. So I want to point that out to you. Finally, some assumptions when you're looking at cost volume analysis. You assume that only one product's involved there. You assume that every product you produce can actually be sold, right? 25,000 units breaks you even at $4, $4 profit margin at a time. But technically, you're still in the hole until you actually sell those. We just do the math as if I'm going to sell them. The variable cost does not have any additional economies of scale, such as buying this many units of raw materials to make those many units of finished goods. We assume that variable cost stays consistent as well. Fixed costs don't change with volume changes, meaning that the fixed costs are the fixed cost. Revenue doesn't change. We're not going to sell it for less money or more money if we make more or fewer units. And then the revenue per unit exceeds variable cost. So the other assumption is that we're selling it for more than it's costing us to make. We're not going to make it for $2 a unit and sell it for $1 a unit and suffer $1 loss every time. Those are assumptions being made. Although, video game consoles, they say whenever the console first launches, they're selling those at a loss just because they'll make the money back in the software sold and such, and then accessories, right? PlayStation 4 cost more money than the sticker price when it launched, but they'll sell controllers for $80 a piece and make their money back pretty quick that way. All right, let's look at the supplementary chapter, because it's actually going to be more keeping the theme from chapter 4. There's more stuff coming out of chapter 5, and in fact, I believe think for a second. Now, your chalk and wire assessment, I believe on this one actually does come from chapter 5, not 5S for this class. So you still want to keep your notes from chapter 5 and 5S for after the chalk and wire becomes available, but the 2 chalk and wire assessments we do come from chapter 3 and chapter 5. So decision theory, this is the idea that making your decision would rely on certain knowable factors, and making the decision there's ultimately right based on probability or right based on using all the inputs you have decision to be made. We're not looking at the results of it afterwards. We're not looking results oriented to tell if we made a good decision, but making decisions and the characteristics of those decisions apply to the design of your product from the previous chapter, the capacity planning from this current chapter, location planning that's on a future chapter, and then deciding between two types of equipment as well, two or more. When you're making a decision, so in decision theory, you lay out possible alternatives, a list of alternatives based on future conditions that are possible, such as if I build at this location or this location, well, there's a chance that they might be building a new bridge soon, but I don't know that, but there's a good chance they'll build a new bridge, and if they do, then this location is probably going to spring up and be a great location for our new factory or retail outlet, right? But if they don't build it, then people aren't going to be able to get to us, and so this other one would have been better, right? So the idea that there's possible conditions, it could be something like, how many people do we schedule on a Saturday at a swimming pool? How many lifeguards do we schedule? Is it gonna, but there's a probability of rain or not, right? So the possible future conditions would have a bearing on the results. And with that in mind, we lay out the list of alternative decisions, and then we lay out what's called a payoff table, meaning a payoff for each of them, meaning what would happen if I make this decision and this is the actual outcome of that future condition. I'm going to make this much money, or we'll have this much demand, right? But if this happens, we'll make this much money, or we'll have this much demand. And then applying ideally some quantitative elements to it, probabilities if we have them, or simply using one of the other theoretical methods or common methods there, which we'll see on the next few slides, to those in order to make the right decision. So the process is identify those possible states of nature. That's what they call them. The possible future situations are called states of nature. Develop your list of alternatives, at least two alternatives, right? Otherwise, there's no decision here. Often with this type of work in your book, it's usually 3 of them, but it could be 2, 3, 4, 5 possible alternatives. Estimate the payoff. Now that might be, like I said, units of demand or money made, or any kind of anything you can quantify. So the payoff is something quantifiable. If possible, estimate the likelihood. This might come from your forecasting team, or the results of your forecast in the past. They were accurate this much percentage of the time, so then you've got this much % likelihood that they're not accurate. And that could be one way to determine the possible states of nature. Otherwise, you could use qualitative elements, and what your gut's telling you. It could be as simple as that, right? But and then evaluate them based on some criterion, some decision criterion, which we'll talk about the different types of those based on the circumstances, and then select the best one. And again, the best is not based on the results. It's based on the using the likelihood of results, utilizing all the inputs we have. So payoff table is the grid where we show the types of alternatives. So building a small, medium, or large facility would be alternatives. The possible future demand, the states of nature. The demand might be low, medium, or moderate, or high. All right, these are the possible futures. And then these are the choices. Do we build a small facility, medium facility, or large facility? Okay. And so when we build this decision table, in this case, they're displaying this. This isn't $10, it's $10 million. They say here, the value in millions that you would make in profit, revenue, whichever. If you build a medium facility and the demand is moderate, then you'll make $12 million. However, if you build a large facility and the demand is high, you'll make $60 million. But if you make all that capacity from a large facility and there's low demand, you're not going to make back all the big investment. You'll actually lose $4 million. So this is how a decision or a payoff table is typically laid out. So let's look at the steps. Identify the problem. And these 7 steps will come important because you might potentially get asked what is step number 3 or 5 or whatever. So the order of these matters, hint, hint, for possible quizzes or exams down the road. Identify the problem, specify those objectives and what criteria you're using, develop the list of alternatives, analyze them and compare results, select one, implement it, and then monitor to see if the right decision was achieved. And then you can use those results to infer on future decisions. Why might you make a poor decision? If you are using all the right inputs, then the decisions could turn out poorly. However, that's not normal. It's more likely than not that you would have good results if you make good decisions. However, you might make mistakes. You might have issue with bounded rationality, which we'll cover on the next slide what that means. We might have an issue with sub-optimization. So these are 3 frequently frequent reasons for poor decisions occurring. So bounded rationality is how much you have available in terms of finances for the costs available, the human abilities, time, the technology available, the information available, anything that you don't have the things you need in order to make the right decision are not there, right? They cost too much to make a good decision because you can't hire a team to do the forecasting for you. You just don't have the right people that are knowledgeable enough about making this part, or maybe that they've called out sick and now you can't make as much, and so your decision doesn't turn out well. There's not enough time to get to implement it before you needed it. The technology just isn't there. Yes, if we could do this, great, but the technology isn't there, right? So those are things that, rational limits of what you can and can't do. And then sub-optimizing is when you have several different departments and they're each optimizing for their department. They're not optimizing for the organization. And so they're making a good decision and it makes their numbers look good, but then the organization doesn't meet their goals for the year or quarter or whatever period of time, right? Which is not good for the organization, right? Sub-optimizing, you're optimizing for the subsystems instead of the whole. All right, 3 types of decision environments. This is going to come up on several questions you might be asked this chapter. There's 3 environmental categories for decisions: certainty, risk, and uncertainty. Okay. Certainty is when we know exactly what's going to happen if we make these decisions. So if I have 2 investments, one gives me a 3% return, one gives me a 5% return, and they are both the same type of investment. They're both, CD or mutual fund or, bond or whatever, right? So if we know the exact outcome, it makes our decision easy. Okay. I'm going to skip risk for a second, but uncertainty means there are a number of different outcomes, and we don't know the likelihood of any of them. However, these 2 seem very similar, risk and uncertainty. However, risk means that you have probabilistic outcomes. There are probabilities assigned to them. There's a percentage of the time this occurs, a percentage of the time this occurs. If they are equally likely, then it's uncertainty. You don't have the probabilities. So while they seem similar, you don't know, anything could happen. If there's any probabilities given to you in the problem, it's decision-making under risk, period. If I say that there's 75%, 25% chance, that's decision-making under risk. If I do not give you probabilities and I say they're equally likely, then that would be uncertainty. Uncertainty has a lot more options because it takes some it takes a lot more managerial decision type making with uncertainty. With risk, you can just apply probabilities to outcomes and choose the one with the highest expected outcome, right? Uncertainty is going to be a little bit different though. So certainty, yeah, we know exactly what will happen, right? Two investments, 3.14% or 3.4%, 5.6%. Well, I'll choose this one. However, let's say that there's uncertainty because there is a risk involved of some kind, but we don't know the probabilities of those risks. Okay. This is uncertainty. Yes, I know it's a little confusing because it says there's risk involved, but again, decision making under risk, that specific term only applies when there's probabilities. So investment one might be a CD, which is guaranteed, but investment two is a mutual fund, which isn't guaranteed. So now you've got, okay, I could do this, but how much do I like to take risks, or do I just want to shoot for the higher possible outcome or whatever, right? So decision making under uncertainty, this is going to be the bulk of it. There's really 5 decision criteria we're looking at in our problems. These 4, which are the 4 different types of decision criteria under uncertainty: maxi-min, maxi-max, Laplace, and minimax regret, which we're going to go over shortly. And then decision making under risk, when there's probabilities involved, we'll do a separate problem on that as well. So maxi-min, you choose the alternative with the best of the worst. This is what you would do if you were pessimistic. You don't think that it's going to be a good outcome. Being pessimistic does not mean you want a bad outcome, though. So it isn't as simple as choosing the absolute lowest number in a table, right? If you look at this table and you look out there, well, the lowest one is -4. I'm not going to choose that one because it's -4 and I'm pessimistic. I don't want to lose $4 million. I assume that the worst possible future is what's going to happen, and I choose the best of the worst. Okay, so if the worst future is going to happen, in which one do I either still make the most in that scenario, or do I lose the least in that scenario? That's the decision under maxi-min. And if you look, maximize the minimums, best, maximize the worst, right? The minimums, maximize the minimums, maxi-min. Okay, maxi-max, choose the alternative simply with the best payoff. Out of all of these listed here, the highest number is 16. So if I was choosing under maxi-max, I'm just choosing that one. Okay, maximize the maximums, the best of the best. That's the one I'm choosing. Okay, and this has to do with the type of decisions, the type of characteristics of your leadership of your company. If they're just a pessimistic person, or the company's chooses to be pessimistic in their outlook to minimize risk, this minimizes your risk. Maxi-min minimizes your profits, but it minimizes your risk. Maxi-max, you're gambling because you could choose that. It might have the best payout, but you're straight up gambling with this one, because usually the ones with the best possible payoffs, not always, but usually those have the lowest negative outcomes too that are possible. Laplace, you just average out all the payoffs for that alternative, and the highest average payoff is what you use. This is you could call this the average payoff, but the person who came up with it, I imagine, had that last name. Otherwise, this is just a term I'm not aware of. I believe it's somebody's last name though. And then finally, mini-max regret. It sounds difficult, but the idea is with what a regret is in terms of decision making is, if I choose this one and something better happens, how much did I regret my decision, right? Or well, I mean, that about sums it up. So let's look at each one of these 4 on its own. Maxi-min, again, out of all these options, a small facility will have 10, 10, or $10 million. So no matter what, I'm expected to make $10 million with a low, moderate, or high future. With a medium facility, I'm expected to make 7 million. With a large facility, I'm expected to make lose $4 million. So the decision here is in the small, if the possible future is low, okay. So the least I'm going to make is, or the most I'm going to make. I'm saying it wrong. If we look at the worst outcome of each one, so the worst one for small is here, or here, or here. That's why they have all of them. The worst one for medium is also here. The worst one for large is also here. They're not always going to be lined up in one column, though. this might be the lowest here, this might be the lowest here, and then this might be the lowest here. It's not, but we're looking at the lowest of them. So small facility, the worst payoff is 10 million. Medium, the worst is 7 million. And large facility, the worst is -4 million. So of those bad possible outcomes, small facility is the one I still make the most on. So I'm going to just go with small facility. I'm minimizing my risk. I'm not minimizing my profits. Okay. If I was minimizing my profit, I would choose to lose $4 million. That's not the case. Again, pessimistic does not mean you want the negative outcome. And I say that, stressing that, because I've still had a number of students just put in, you know, well, how much would I make if I would use the maxi-min? They would put -4 million right here. So I understand the confusion. That's why I'm taking extra steps on this video to stress that you don't want the bad outcome. You just think it's going to happen. So if that does happen, which one do I still make the most or lose the least on? All right. Maxi-max. Yeah, you don't really have to look. It has you looking at each of these individually, but with maxi-max, it's just the highest of all possible outcomes. So yeah, you could compare 10 to 12 to 16, but honestly, you just look at the whole table and the highest one matches to large, so you just choose large. Simple as that. Average, we just have to add them together and divide by 3 or however many possible futures there are. The small facility, the average of 10 million plus 10 million plus 10 million is 10 million. Surprise. Medium facility, this averages out to 10.3 million. Large facility, this averages out to 4.6. So of these options, that's the highest of the averages. So we choose medium. So far we've chosen small for maxi-min, large for maxi-max, and then with Laplace, we've chosen medium facility. So you really, as a company, would want to decide ahead of time which decision-making criteria you are as a company. We're just always going to average it out. That's going to be our policy. We're always going to take the least risk. That's our policy. We're always going to go for it, all in, and risk losing 4 million or only making 2 million just to try to make 16 million. Because you're not likely, the average is so bad. Minimax regret. Minimax regret, a little bit longer of a step because it requires you to make what's called an opportunity loss table or regret table. I always called it an opportunity loss table. This book calls it a regret table, probably to simplify it and make the word regret match. The decision between what decision you did make and what the best payoff would have been. So here's how that works. If I build a small facility and the future ends up being low, I don't regret that decision at all. And so your regret table will show that I regret it for $0. Okay. The demand was low. I built a small facility. Yes, I don't regret that decision at all. Right. If you've ever played poker and you folded your hand and then with a big draw coming, right? I have a flush draw, but I'm going to fold to a big bet, and then the flush doesn't come in. Yes, I don't regret that. I didn't make any more money, but I didn't lose any more money, and I'm very happy that I folded my hand. Right? Don't regret that one bit. So you've got low possible future, and you decided to build a medium facility. Okay, I made $7 million. Sweet. Oh man. If I'd only built a small facility, I would have made $10 million. I regret it to the tune of 10 minus 7, which is, I regret it to the tune of $3 million. That's what you put in the regret table, and so on for each one of these. You match up the decision you made with the highest total in that column. So on the final one here, I built a large facility. I lost $4 million. If only I built a small facility, I would have made $10 million. So the difference between 10 and -4 is 14 million. So my regret is to the tune of 14 million. And I do the same thing with this column. I do the same thing with this column. Once I have built my regret table here, okay, once this is done, I take one last step, which is to compare the highest values here. And unlike the pessimistic approach, this is not a pessimistic approach. I want the lowest possible amount of regret. I do not want to regret my decision. If I look at for small facility, the most I might regret it is here, $6 million. The most I might regret building a meeting facility is here. That was a really good arrow. I'll just draw a circle. Most I might regret it is here, okay? I might regret it for $4 million. If I build a large facility, I might have $14 million worth of regret. That's a lot of regret. So I choose the one with the least amount of regret. And that decision is medium facility. So those are the 4 types of decision-making under uncertainty. And then our final decision-making type would be if we have risk. This is where their probability is assigned to us. And we use a technique called expected monetary value. This is the likelihood of the payoff when I average out the, think of it like a weighted average, okay? I'm going to use a sum product in Excel, and I'm going to multiply the odds of a low demand, or the odds of a moderate demand, and odds of high demand, okay, for large facilities payoffs, medium facilities payoffs, large facilities payoffs. Did I say large twice? Small, medium, and large facilities payoffs. Then I add those products together. I sum those products, and then I just total them up, and that's going to tell me the expected monetary value. If I was to make this decision 1 million times, what the expected value would be based on those probabilities. So if you are not risk averse, if you're risk averse completely, you would still go back to the max-min approach and say, I'm really pessimistic. I don't want to risk anything at all. If I'm risk seeking, if I'm very optimistic, I still choose the maxi-max. But if I'm neither, if I just want to take a smart approach because I have the probabilities, you should choose EMV. And so you just you do a weighted average effectively, which is 0.3 probability of low times 10 plus 0.5 times 10 plus 0.2 times 10. Well, they're all multiplied by 10, so it comes out to 10 when you add them together. All right. $7 million times 30% plus 12 million times 50% plus 12 million times 20%. Add those together, you get 10.5. And you can see the EMV of a large is very low at 3. So in this case, you end up choosing medium facility based on EMV. We're going to go over that in more detail on the other video. Decision tree is not something I'm going to have you do in this class, but I want you to be aware of what that looks like. Decision tree is another way of writing EMV. However, you're able to expand the trees when there are multiple decisions that are not the same amount of possible outcomes. So in this case, we build large or build small. So we just follow the branches of that tree to its conclusion at the end. If I build a small tree, there is low demand, that's my payoff. However, it's a high demand, but based on whether we did nothing or paid overtime or expanded, these are my payoffs, and so on. You build all this tree out. It's another way of graphically looking at it. I believe that with the purposes of this class, using the EMV on the payoff table here is just a much cleaner, faster way of doing it. So we're going to skip this. Perfect information. I want you to imagine in your mind's eye an envelope, and in that envelope contains the future. Okay, it says in that envelope there's going to be high demand. Got that? All right. So the idea with expected value of perfect information is if I make a decision on EMV without the knowledge of that envelope, how much am I expected to make? If I had perfect information, if I knew exactly what the outcome would be, which decision would I make, right? And so I can make a small facility, medium facility, or large facility decision because I've got perfect information, right? And so I would have an expected value of the best possible outcome, right? Knowing what that envelope might contain. So the idea of expected value of perfect information would be, what's the value of that envelope, okay? And we're going to go into this in the Excel file, so I'm just going to briefly touch upon it. But the general idea is, and I think the envelope analogy works, because let's say I did all the math, and let's not go through the math in this video because it's just a little bit long. But the idea is, without the envelope, just based on what we did before, I would make $10.5 million. However, if I do the math with perfect information, so knowing instead of taking the EMV of each of these and taking the highest one, I would take 30% times the best, because I know the envelope says low, then I'm going to choose the best payoff for low. 50% times 12, because if the envelope says moderate, I'm going to choose medium, and then 20% times 16, because if it says high, then I'm going to choose large facility. So I average that out. So 30% times this plus 50% times this, 20% times this equals 12.2. So with perfect information, $12.2 million is what I'd make. Without it, 10.5 is what I would make. Therefore, the expected value of that perfect information would be 1.7. Now, what does this actually pertain to in real life? Forecasting companies that specialize in doing better forecasting of environmental scanning and possible futures. How much would I be willing to pay that company to do this research for me? Okay, that's the idea. If I paid up to $1.7 million, I'd be expected to break even. Now, obviously, I don't want to do that. Why would I do that? Because there's risk, extra risk involved that it doesn't tell me the right amount, right? So therefore, I would probably want to pay maybe a quarter of that, and to make that profitable. All right, then yeah, that's it. So that's it for this slide. This PowerPoint. I've got the full PowerPoints for both 5 and 5S on Blackboard, and then also also I'll see you guys on the practice problems video. Thanks, everyone.